So one of the important things in chemistry is to record measurements to the correct number of significant figures. And just to kind of review on how we get the number of significant figures from measurements, it involves two things. It involves the certain digits plus one uncertain digit. And so the certain digits are based on the smallest tick mark on the measuring device. So you look at your device, you determine what's the smallest tick mark represents, and that tells you how precise your certain digit is. So when we look at this Buret, you'll see that the large tick marks, we go from 10 to 11, so that's 1 milliliter, and there's 10 tick marks between 10 and 11, which is the tens place, so say 0.1 place. So that means our certain digits go to the tenths place when reading a Buret. So if I was to say the certain digits are in green, the green spaces represent the certain digits. Now the estimated digit is generally the placeholder to the right of the smallest certain digit. So you find out where the last certain digit is. So in this case, the last certain digit is at the tens place. So that means the estimated digit would be in the hundreds place. So when you record this measurement on the Buret, you would record it to the hundreds place. So the certain digits should always be the same, but the estimated digit may be different between different people because it's based on the observer. So it's wherever the observer thinks that he or she estimates that digit. So estimated digit can be different, certain digit are the same. So generally, once you find the smallest certain digit, then the placeholder to the right of it is the estimated digit. So when we're reading this Buret, the smallest certain digit is the tenths place. The estimated digit is the hundredths place. And that's a very common mistake students forget, is to include the estimated digit. Now when you're reading volume from glassware, you'll see it forms a curved surface, which is referred to as a meniscus. And so you always want to read it at the minimum of the meniscus. That's where you record the volume of the liquid. Now with a Buret, it's an interesting piece of glassware because with a Buret, you read from top to bottom. So you start from the top and you go to the bottom, because as you see, the top is 10 milliliters, the bottom is 11. So first we want to determine the certain digits. So the certain digits are based on the tick mark. So we know for certain it's 10, 10.1, 10.2. So our certain digits are 10.2. Let me write it down here. Now for the estimated digit, the common practice is that if the volume is close to a tick mark, the estimated digit would be 0. If the volume is between the two tick marks, the estimated digit is 5. That's common practice that scientists use. However, if you put a 3 or a 4, that's fine as well, but the argument is that it's very hard to discern between 0.05 and 0.03 or 0.04 milliliters. So common convention is if it's between the two smallest tick marks, we label it a 5. If it's close to a tick mark, the estimated digit is a 0. So using that convention, since the meniscus is between two tick marks, our estimated digit would be a 5. So our measurement is 10.25 milliliters. So the measurement using a Buret would be recorded down to the hundredths place. So that's how you record the number of significant figures from a measurement. So the last bit of this chapter deals with the discussion of density, which is a physical property. It's actually an intensive physical property, so it doesn't depend on the amount of matter. So that's what we're going to look at next, is density and some calculations involving density. So density is the amount of mass per given amount of volume. Again, it is a physical property. To be more specific, it's an intensive physical property. And what that means is it doesn't depend on the amount of matter present. So for example, the density of aluminum is 2.7 grams per centimeter cubed. Whether you have 1 pound of aluminum or 3 pounds of aluminum, the density is the same. So density doesn't change with amount, so it's a intensive physical property. So if your property doesn't change with amounts, it's an intensive physical property. To give you some other examples of intensive physical property or properties are things like boiling point, melting point, color, malleability. So malleability is the ability to put something in sheets. What else? Odor. So these are things that don't depend on the amount of sample present. So it doesn't change with the amount. So something that would change with the amount is something like mass. So the more of the substance you have, the more mass you have. So mass changes with amount. Also volume changes with amount. So the more matter you have, the more volume you're going to have. And so those that do change with amounts are referred to as extensive physical properties. And these change with amount. So if you increase the amount, you're going to increase those physical properties. And the two most common examples are mass and volume. So with physical properties, you have two types: intensive physical property and extensive. Intensive doesn't depend on the amount, such as density. Extensive does depend on the amount, such as mass and volume. That's just a little side note there. Now with density, the equation is mass over volume. The SI unit is kilogram per meter cubed because the SI unit for mass is kilogram. The SI unit for volume is meter cubed. And this is referred to as a derived unit because it's derived from, or derived SI unit because it's derived from mass and volume. Now, generally in the lab for solids and liquids, we use gram per milliliter, and for gases, we typically use grams per liter. And it's in labs also you can use it as a way of distinguishing between different substances because different substances have different densities. So for example, iron is 7.86, copper is 8.92. So if you measure the density of your substance and you got it close to 8.92, you could say it's going to be copper instead of iron. So every substance has its own density. Now, typically with the phase states, solid is the most dense, followed by liquid and gas. However, there's some exceptions. One is water, where the solid is less dense than the liquid. So if you ever put ice in a cup of water, you see that the ice floats because it's less dense than the liquid. Now, if you keep volume constant and you increase the mass, you're going to increase its density. So there's a direct relationship between increasing mass and increasing density of your substance at constant volume. Now, if you're at constant mass and you increase the volume, you're going to decrease its density. So they're inversely related properties. So if you increase the volume at constant mass, you're going to decrease the density. And one way you can determine the density of a substance is you plot its mass on the y-axis versus volume on the x. So if you plot mass versus volume, you get a linear relationship. The slope equals the density of your substance. Slope is defined as m. So you determine the slope of the line, that will tell you the density of your substance. So the steeper the slope, the greater the density is. Now, qualitatively, we can look at a picture and kind of get a qualitative assessment of the densities of different substances. So for water, generally water is usually referred to as 1 gram per milliliter. So here we have this picture of some oil, water, and syrup. And we know that water is roughly 1 gram per milliliter. So if something sits above water, that tells us its density is less than 1. If something sits below water, that tells us that its density is greater than 1. So something that is more dense is going to sink. Something that is less dense is going to float or be above water. So by knowing the densities of, say, water, you can determine or qualitatively determine the densities of your other substances. So we know oil here has to be less than 1. And for syrup, we know that its density is going to be greater than 1. Now, if its density was 1, then it would be kind of suspended in the water solution. Or the water is not really a solution. And so one way that we can determine the volume of a substance, especially if it's irregularly shaped, is by water displacement. So this technique shown in the bottom right-hand corner is referred to as water displacement or volume displacement method. So what you do is you will go grab a graduated cylinder, you fill it with water, so this is the initial. Then you add your substance into the graduated cylinder. You're going to see the water level rise. So this is our final. And the volume of the object is just a difference between the initial and final marks on the graduated cylinder. And so this is a way that you can determine the volume, especially of an irregular shaped object, is by using the water displacement method. So again, you get a graduated cylinder, you fill it with some water in it, you take the initial reading, you add your object, the water level rises, and you take the final reading. The difference between the two gives you the volume of the object. Now you have to make sure that your object does not dissolve in water, or else it won't work. And this is a common technique that we use to measure volume of especially irregular shaped objects. For example, a rock could be a good example. And so we have a type of calculation. Let's say we have 43.7 milliliters of ethanol, and it has a mass of 37.32. What's its density? Well, density is just mass divided by volume, and so we get a density of 0.789 grams. So that's what you would do in the lab. You would take a sample of ethanol, measure its volume, measure its mass, and you can calculate its density. Now, a derivation of this is, let's say we want to know what volume of ethanol would have 116 grams. So in this problem, we will have 116 grams of ethanol needed for a chemical reaction. What volume of the liquid would be used? So we have to rearrange the equation to solve for volume. So what we do is volume is equal to the mass divided by density. So the density is 0.789, the mass is 116, so we'll need a volume of 147 milliliters. So volume is equal to mass divided by density. Mass is equal to volume times density. So this is how we can manipulate density to solve for either the volume or the mass. Now we're going to look at some examples of problems involving density. So the first example is more of a qualitative example. So here we have this picture that has the density of 7 different liquids plus air. And we know that water has a density of 1 gram. What would be the density of the syrup? So we look here. We know that water has a density of 1. So what that tells us is that anything above water would be less than 1. Anything below water would be greater than 1. So we're looking for the syrup. So we know that if we're looking for the syrup, anything less than 1 would not be an answer. So we can go ahead and get rid of A, B, D, and F. And the reason we can get rid of those is that all of those values are less than 1. And so if it's less than 1, it wouldn't be the syrup, because to be the syrup, it has to be greater than 1. So now we have 3 choices remaining. Now the most dense substance is honey. So honey would have the highest density. So we know that since honey would have the highest density, it would not be G, because G is the highest density. Next, we have to decide between what's the density of the dish soap and the syrup. Well, since the dish soap is above the syrup, the dish soap would be less dense than the syrup. So therefore, the density of the syrup would be 1.25. And so we were able to deduce that based on knowing that water is 1 gram per milliliter. So this was a qualitative example. Now we're actually going to look at some calculations involving density. So here's a typical density problem. We have Frodo likes to drink mead, which is a fermented honey. If mead has a density of 1.357 grams per centimeter cubed, mead has a density of 1.357 grams per centimeter cubed. If Frodo has 46.2 pounds of mead, how many liters is this? A little bit of grammatical error right there. So we want to know how many liters of mead does Frodo have? And he has 46.2 pounds. And so we're given the density and we have the weight of the meat. So what we can do is, and the density is in grams per centimeter cubed. And we know from density that to determine the volume, volume is equal to mass divided by density. But in order to use the density equation, mass has to be in grams because the density is in grams per centimeter cubed. So over here to the left, it gives us this conversion factor of pounds to kilograms. So what we're going to do is we're going to take the pounds, convert it to kilograms, convert it to grams, and then we can convert it to centimeters cubed, and then to liters. So that's what we're going to do is we're going to take the pounds, convert it into kilograms, because that's the conversion factor that was given to us. Then from kilograms, we can convert it into grams. Once we have it in grams, we can use the density equation to find the volume in centimeters cubed and then convert to liters. So we need a few more additional conversion factors. We need to know how many grams in a kilogram and how many centimeters cubed in a liter. So 1 centimeter cubed is the same thing as 1 milliliter. So if we want to know how many centimeters cubed in a liter, we know that there's in 1 liter, there's 1,000 centimeters cubed. Also, we can take our density and write it as a conversion factor. We can say 1.35 grams equals 1 centimeter cubed. So now we have all our conversion factors. We know our process we're going to do. And again, there's different ways you can approach this. This is just one way. So now we're ready for our train tracks. So we're starting off with pounds. Now we want to convert to kilograms, so since we're starting with pounds, pound goes on the bottom, and our first empty train track, kilogram, goes on top. So that's the first step, convert to kilograms. Then we want to convert to grams, so since kilogram is on the top, in our next empty train track, kilogram is going to go on the bottom, and grams will go on top. So we've done the second step. Next, we want to go from grams to centimeters cubed. Here we have to use that 1.35 grams equals 1 centimeter cubed. So since we're starting with grams, in our next empty train track, grams goes on the bottom, and centimeters cubed goes on top. And then lastly, we want to convert to liters. Since we're starting with centimeters cubed on top, our next empty train track, centimeters cubed goes on the bottom, and liters go on top. And now you'll notice that everything cancels but liters. Also, to make the calculation easier, since there's 1,000 here and 1,000 here, we can get rid of the thousands. They cancel each other out. So now you multiply everything on top, divide by what's on the bottom. And we get equal to, and the calculator tells me 15.4 liters. So now we got to look at significant figures, see how many significant figures we should round to. So 1 kilogram to 1,000 grams, that's exact. 1 pound to 0.45 kilograms. Remember, pound is standard. Kilogram is metric. So we're going from standard to metric, so we have to include significant figures. So this one has 2. 1 centimeter cubed equals 1 milliliter. That's exact. 1 liter, 1,000 centimeters cubed. Exact. And 1.35 grams equals 1 centimeter cubed. That has 3. And then 46.2 pounds has 3. So our answer should have 2 significant figures. So we should round this to 15 liters. So that's how many liters that Frodo has of this fermented honey drink. So here we have another density problem. We have a piece of mithril, a mystical metal found in Middle Earth, is added to a graduated cylinder with an initial volume of 15.7 milliliters. The volume of the graduated cylinder increases to 26.3 milliliters. If the density of mithril is 4.2 grams per milliliter, what's the mass of this piece of mithril in micrograms? So we have a piece of this mystical metal. We add it to a graduated cylinder. The volume increases. If we know the density of this metal, what's the mass in micrograms? So before we actually do the calculation, let me draw a little sketch of what's occurring. So initially we have our graduated cylinder. It has 15.7 milliliters. We then add our piece of metal, and the volume increases to 26.3. So this is the final state. So in this graduated cylinder, we have our mystical metal. And so from this, we want to determine what's the mass of that piece of metal that was put in there in micrograms. So again, we're given the density. The density is the way that links us between mass and volume. So what we're going to do is we first have to find the volume of the metal. And we're going to find the volume of the metal from the initial and final volume of the graduated cylinder. Once we get the volume of the metal, we're going to use the density to find the mass of metal. And it's going to be in grams. And then we're going to convert that to mass in micrograms. But again, to find the volume of the metal, we're going to have to use the difference in volume between the two graduated cylinders. And it's always final minus initial. So what conversion factors do we need? Well, we know that since the density is 4.2 grams per milliliter, we can write it as 4.2 grams equals 1 milliliter. And then we need to know how many grams in a microgram. So 1 microgram is 10 to the negative 6 grams. So now we can determine the volume of the metal. So volume of the metal is the final volume minus the initial volume. $26.3 minus 15.7. And we get 10.6. So the volume of the metal is 10.6 milliliters. So now we can set up our train track. So we're starting with the 10.6 milliliters. So since we're starting with milliliters on the bottom and in the next empty train track, milliliter goes on the bottom and gram goes on top. Next, we want to convert grams to micrograms. So gram in our conversion factor of micrograms to grams, gram goes on the bottom, microgram goes on top. Now we multiply what's on top, we divide by what's on the bottom. And so what you can do is when you multiply what's on top, you get 44.52. And what's on the bottom is 1 times 10 to the negative 6. So what you can do to make it easier, if we put the top number in scientific notation, get 4.452 times 10 to the first So when you divide, you subtract exponents. So 1 minus a negative 6 gives us 7. So this would be 4.452 times 10 to the 7 micrograms. And that's just an easier way to do it, because if you do forget the parentheses on your calculator, you get some, you may get the incorrect answer. So this is just a good way to do it. So we just multiplied what's on top, took the top number, wrote it into scientific notation. When we divide, we subtract exponents. We got 10 to the 7th. So there's 4.452 times 10 to the 7th micrograms, but we're not finished yet. We got to convert to the correct number of significant figures. So our initial volumes both had 3 significant figures, and even our volume of metal had 3. Because some may say that since this is a separate operation, you have to take the correct number of significant figures from the answer in this step and include it, because this is a separate operation from this one. Others may say that since we're doing both of these together, we just look at the initial numbers, determine the one with the smallest number of significant figures, and use that. But here it's okay, they're both 3. Now our density has 2 significant figures, and since it's the micrograms to grams is metric to metric, it's exact. So our answer should be rounded to 2 significant figures. So after the 4 is a 5.2. Since 5.2 is greater than 5, this would be 4.5 times 10 to the 7th micrograms. So this would be the mass of that metal in micrograms. Nope, that was it. So that's